feeling and math teacher as a credit card is a good idea. You can max it out.
Look, I'm a student.
Yeah, that's true. I'm not as poor as you.
Are we looking at the finishing of Leibniz as Tesla?
What? What did you say? Did you hear
Are
Simon?
we in the middle of finishing off Leibniz as Tesla?
The what is?
Leib-
Leibniz. No, I finished it in a second. I told you it's a specific example of Dirichlet, and we were done.
How can you give us more homework with the last homework? It's
It happens in every class.
When is this sponge?
Sammy isn't just melting down. Oil here is bubbling
I think
while
it's
he melts.
next Thursday.
Oh,
Okay.
it's gotta give.
It's either computer science, math, or you.
What's going to give up?
Yeah.
What about Ulpan and the Yom HaVe'ah that I'm taking next Thursday?
And the Israeli IDF.
Yes, what's
The IDF, Israeli IDF is silly. The IDF. Yes.
Israeli is our defense force.
Yes. Yeah, see, we did approve immediate from the Israeli.
That's what we call
It proves
this
by
great
reference.
maths.
Yeah.
I mean, sure.
Yes.
Uh,
Proof, but if you don't get it by now, give up. No, sorry. But it's not really hard. It's okay.
So why is that in a separate proof for it then? If it's
Uh,
literally derivation.
That's a good question. Many times someone thought about the specific case first, and then they made it more general. That's one reason. In lecture, I'm not sure what is the reason here, but in lectures, sometimes the Dirichlet proof is much harder than just Leibniz. So in engineering, I'm just doing Leibniz. I'm not doing Dirichlet. Oh. Okay. Lecture 14, we are at functions. So we wish to study calculus of functions, of real functions. What does it mean? Functions from the real field to the real field. So in discrete mathematics, when we learn about function, it's in a much more general case because the functions could get any set as a domain and get any set as range. Here, the domain and the range are always the set of real numbers, and maybe the domain, the actual domain, is a bit less than that because you have the תחום הגדרה. How do you say תחום הגדרה in English? Do you know?
it's
Domain
of definitions.
yeah, but that's again later. Let me just make sure of it because it's weird. It's also cultural. In discrete mathematics, I'm not sure, but usually we define the domain as a set where the function is defined over all the domain. In high school, we said the domain is the real numbers, and then you have תחום הגדרה, which is the set where the function is actually defined. I'm sure it's going to say domain of definition, but still trying. It's, yeah, domain of definition, fine. But it's silly because it says in English you usually say domain, or in the full name domain of definition. That's completely unhelpful. In any case, the point is, if you look at square root of 2, is it a function from the real numbers to the real numbers? in discrete mathematics, you'd say no, because it's not defined over all the real numbers. Okay, that's it. I'm not even writing it because it's not that interesting. It's just a little bit of difference in notation and naming from discrete mathematics. Functions are all from R to R, and they will have domain of definition where they are defined. Yes. Why did I need one? Ah, you're in my Facebook. No, you're not in my Facebook. You're in my ChatGPT. Oh, yeah, that's political. Yeah, I can show you. So, if you read the news, then you will understand what I meant here. Okay, that's political. I allow myself to be political when I say both sides are wrong. I think that's enough that's fine to tell to the students. Okay,
I
it's
hate them
not
all.
choosing a side.
Uh,
Yes,
Is
you get to hate them all. It sounds like a Pokemon.
yeah, you're not racist. You hate each race equally.
Yes.
So is there like a separate course in the university that's real analysis, which is like because in
Why?
in the
This
US
is real analysis.
in the US there's like calculus 1 and 2 and there's real analysis, but I think it's what we did before.
I think if I understand correctly, that calculus is what we would call pre-calculus and usually don't teach. And real analysis is really calculus. I think that's the thing. By the way, another funny thing, there is actually a course named Real Analysis in Tel Aviv, I think, which is much more complex than calculus. It's in Israel, in Bar-Ilan, I mean, we call it modern analysis.
Mm.
But I think
Why is it
from
more
what
complex?
what
Why is it more complex?
modern analysis is much more complex. It's much more general than just the definitions you see here. It has to do with measure theory and stuff like that. Yeah,
Okay.
measure theory. There are more complex things in calculus than what we do. But what we study in the sense of calculus, it's almost everything there is to study at this field. At this, I don't know, with this definition, let's just say, with the definition of the limit we saw and the definition of derivatives that we will see. So that's the most that anyone is doing. But there are other definitions, more general, and then you can continue to modern analysis. Okay, so we wish to study calculus of real functions. What would that entail? That would entail limits, which we'll start today and do quite quickly, since most of the heavy lifting was done in sequences, and here it will be either similar or using sequences. And after we'll have limits, we'll have the concept of continuity, then differentiability, so these are still a part of, in my mind, the building blocks of the subject. Okay, and afterwards, if I'm not forgetting anything, then we'll move on to actual results. Actual results, which I call so let's do GPT again. I know what you will answer, which I call analysis, חקירת פונקציות.
Function analysis.
This what?
Function analysis.
Yeah, analysis of function. And L'Hopital, L'Hopital, and Taylor. I'm not sure we'll get all the way up to Taylor, but if not here, then in calculus too.
Taylor series.
Taylor series we cannot complete here, but Taylor polynomials, it's like the start. Not sure if I'll put it in parentheses because I'm not sure we'll finish it. I'm pretty sure it's not even in syllabus, but if I'll have time, then I'll start talking about it as well. But what I mainly wish to frame here, it's the actual result. It's the theorems we study about functions, and I call all of them the analysis of functions. Okay. And and also we will do a side quest to define the trigonometric functions. And why am I calling it side quest? Because the subject of the definition of trigonometric functions is actually geometry. That's the way we define them. But I think usually we assume that you know them from high school. A lot of things I assume you know from high school, even though you don't know and expect you to figure out on your own. But trigonometric functions, I think usually, even if you remember from high school, you don't understand it completely. And there are some proofs around it that you really need to understand the functions. So at sometimes I'm saying, okay, let's learn about the trigonometric function. We have one class about it. Usually between continuity and differentiability. Not promising, but probably there. Okay, so that's the rest of the course, basically. And now we'll start. We will start with limits of functions. And first thing will be an example for discussion. And if you remember, we did that very same thing with limits. I gave you a few limits with sequences. I gave you a few sequences and I asked what are the limits and we talked about it. So it's something a bit similar. Look at the following function. The function f of x is when what I'm going to be crazy. Function f of x, because it's an example from Infi2, but you have all the tools to understand. It's the limit as n goes to infinity of the sequence x to the power of n. So for each x, I take this sequence and calculate its limits. For instance, what is f of half? Close, but not at all. Right, 0.
It's either going to be 0 or infinity, no?
Maybe. We'll see. Okay. But do you agree that f of half is 0? Right? Because the limit of the sequence, I like it. I think I will start doing it. And this example of the sequence equal half to the n is 0. Agreed? Mm-hmm. What about x equals -1? No limit. It is outside the domain, the definition. Domain function is not defined over this number. Read
Why?
Because then
minus one to the end does not have a limit. Right? Minus one, one, minus one, one, it does not have a limit.
Oh, it-
I would
What?
No, I said I see.
Yes.
I would have asked first when x is 2 and then x is minus 2 and then the interesting part is
When you will be elected, you can decide what to ask. Okay. Also, when x is 2, f, the function f is not defined. Why is it not defined? Sometimes the student asks me, why not say that f of 2 is infinity? Remember, infinity is not a number, but in any case, it's definitely not a set of
So is it just a dot at
What?
the center at the origin? No, it's like a.
No, it's
like
not.
a really, like.
It's
powerful-
not a dot. This is the line. The center is 0. And infinity, where is it? In Hebrew, you say Ein Sof. I always laugh at the students. Say it's literally there in the name. Ein Sof. There is no end. So it's not a number. In
No,
any
I'm
case.
trying to think on the graph. Like, is it just like
It's not
at
a
the point at
number.
the fin- No, the whole graph. What does the whole graph look like? Just a point at infinity and then.
I'm not getting anything apart from the group. But okay.
is this graph even continuous?
And
Well, it can't be. So then it's
we
just
didn't
like-
learn in continuity yet.
Yes, I know.
Okay. What is f of 1? Last. What is f of 1?
It's undefined.
It's 1. 1 to the power of n is the constant sequence 1. Agreed? And now my question is, what is the limit as x goes to 1 from the left of f of x? I write it in words. Words. The limit of the function as x tends to 1 from the left. So, could say we didn't define limit of a function yet, you will be right. I told you this is the first example to understand what do we ask and how do we wish to do it. So first of all, philosophically, okay, it's also BH. Philosophically, the limit of f of x as x tends to say x0 is the y value of f in the vicinity, let's say, in the vicinity, didn't like it yet, vicinity of. The thing is, it's not only that I find that I can't write in English, but I also don't pronounce the words correctly.
No, I
Right.
was to say vicinity.
Yeah, but it's vicinity, yeah.
It's just the way that you pronounce words.
It's like
It-
often.
English isn't a phonetic language like Hebrew is.
Yeah, it's true, it's true. I
Also,
like
the
how
American
English
is
say
like
bottle
Hebrew is-
water
Uh-huh.
versus American bottle water versus Hebrew, which is bottle water. Okay.
Yeah.
Is the y value f in the vicinity of x0. Vicinity is not defined just as the the limit of sequences were. When I'm saying in infinity, what is the value of the sequence in infinity? So again, I'm asking, what do you mean vicinity? So what would you say the limit here is?
1, 0.
So either 1 or 0, right? Okay, and why would you say 1?
Because when you put one into lim f of x, you get one.
Sammy
So
says,
because when you put one into f of x, you get one. So if it's
Sammy
ending,
says that since f of 1 is 1, then obviously the limit would be 1. The function is defined, so there is no worry.
it just stops there. You're like, yeah, it's that simple.
Yes. He's obviously wrong, right? Thomas, like this,
Yes.
says that the limit is 0 cents. Now tell me why.
Because we are raising the numbers to infinity, the distance from 1 to whatever number we're getting is always the distance from 1 to 0.
I didn't understand the
So,
word.
because the difference between raising 0.5 to infinity and 0.9 to
Why
infinity,
infinity?
because we are
I meant, okay, I see what you mean, raised to infinity, you mean the power of n.
yeah.
Okay, so continue again, now I'm seeing what you're talking about.
Because we're raising both to infinity, the distance between them is practically 0, not literally 0.
So the distance between what?
The different, like the different terms going from 0 to 1, the distance between them in practically 0 because you're raising them to infinity.
So, since I did not
Understand?
understand. I'm not sure why you're talking
You-
about the distance
You
between
can,
the numbers.
you can try your explanation.
How I'd say is as you increase x up towards 1, so 0.5, 0.678, etc., infinitely close to 1, the f of x value is getting closer and closer to 0.
What's your name?
Rafi.
Rafi. Rafi, like
F,
Rafi, like that.
I at the end.
Oh, right. Rafi helped and said that for the numbers before 1, the value is 0. I would say that between, I don't know, 0 and 1, that is a vicinity of 1. Make sense? And we asked about the vicinity. So Sammy says, what is more vicinity than the actual number? And they say, what is more vicinity than all of the numbers next to the number? Okay. So obviously Thomas and Rafi are correct and Sammy is not. It's nothing personal. And I'll tell you why. There is no sense in having limits be the same thing as the image of the number. The limit should make us be able to grasp a different concept. And then later, when the limit is actually equal to the value, not actually equal, when the limit is equal to the actual value at the point, what is it called? If the limit is 1 and the value is 1, what would we say about the function?
Constant, continue.
No, continuity. Exactly. That's continuity. So in able to define continuity, we have to separate two things. What is the actual value and what is the limit? Okay, it's all a matter of definition. I'm not proving it because I'm explaining to you why they gave why they defined the things the way they did. Because we wish to talk about where is the function going to and where did the function actually got to. Okay, when the limit is equal to the actual value at the point, that will be called. It's a very literal definition. If the limit is equal to the value, that's the definition of continuity. That would be called continuity.
So the graph, okay, I was completely wrong. The graph is gonna look like from 0 to 1, it's just gonna be flat,
Yes,
and then
exactly.
a point at 1, and that's it.
Yes,
Okay.
yes, exactly that. And I will do it in GeoGebra.
Will it even fly up from 1, or is it just a point up?
No, because like I said, it won't fly up because every number infinitely bigger than 1, it will also be, it will already be infinity. So the graph is basically f of x is if x is between -1 and 1, the value is 0. And if, right, so do that.
Consider a limit of limiting algebra. G of x is if x equals 1, 1, otherwise it has less. Oh, should I. Oops. Okay. You see? There's a small point here. I don't see it. Now you see, right? That's the function. Okay, between -1 and 1 is 0, and at the point 1, the value is 1. That's a not continuous function. Agreed?
Like looks like a guy with a missing an eye.
We appreciate your imagination here.
We appreciate this, Sabios. We're not at all contacting the police right now.
Yes. He doesn't have an eye.
Yes, that's the problem. He doesn't like complex numbers. Sorry. That was the main joke. Right? So that's what we wish to define. Okay. And let's do a few more examples. Let's look at something rather easy. What is the limit as x goes to minus infinity of e to the power, I could do infinity, e to the power of 1 over x. What do you suppose that would be? And you can use the reasoning we spoke about in sequences. We have a reason to do that, but if x goes to infinity, then 1 over x goes to 0. So it's e to the 0. Grid? Using arithmetics, most of the theorems of arithmetics other than limit arithmetics other than the ratio test will hold with function as well. So it's 1. What would it look like on the graph? When the x goes to infinity, the y value would be close to 1. Let's look at it and what's it called in high school.
What do you mean?
Maybe we'll just
Inverse
use
square law.
it. No, let's write the function. That is the function. Okay. We'll speak quite a bit about this function, to be honest, because it has many different interesting limits. So this behavior, as x goes to infinity, the value of the function, the y value tends to 1, agreed? And what do we call the graph of the function? This line here, y equals 1? Asymptote,
Yeah, I was about
exactly.
to ask if we're gonna define asymptote.
So that's that, okay? I'll write it. I usually don't define asymptote in this course because it's a high school thing. And the actual interesting concept is limits. But
When
just
you
to make the
say it's
connection.
a high school thing, we don't really use it much in calculus.
We use limits. We don't have to name it like children in kindergarten. We call it asymptote. It's just the limit of the function.
That's
Okay.
the
Actually, actually, we say y equals L is an asymptote. I'm not even sure how to write asymptote. Asymptote. Simp, yes. Is an asymptote at infinity of the function f of x if and only if the definition, the limit as x goes to infinity of f to the x is L. There are also vertical asymptote, that's another definition. Okay, that's the horizontal asymptote.
what the differentiation of bottom fraction is.
The what?
You differentiate it and then the bottom fraction is equal, you make the bottom fraction equal to 0.
A bottom fraction?
Like the denominator.
When the bottom.
Sorry, my bad, that was a really bad explanation.
Bottom fraction, the
denominator
denominator,
of-
bottom
the
fraction.
denominator of the.
It's 0, but it doesn't,
Work for everything.
it doesn't promise you, it doesn't ensure you there will be a vertical asymptote because 0 to 0 could be a finite number. But yeah, okay. In any case, also is interesting to look at limit as x goes to 0 of e to the 1 over x. What do you think about that?
Depends on the domain.
What do you think?
Wait, 0, sorry.
So first of all, we cannot plug in 0, obviously, but that's like I said before, I'm not expecting to. The limit is about the vicinity, not the actual point. So we're talking about numbers close to 0. 1 over x. If x is close to 0, what will be 1 over x?
Negative or positive?
Yeah, it depends on the side. And you can also see it clearly on the graph. On the right side, what do we expect the limit to be? Infinity. And on the left-hand side,
0.
0. Right? Surprising, but that's fact. Let's see why. Okay. So we have e to the power of 1 over 0. And I'll keep it with a question mark because it depends. It depends on the sign of x. the limit when x goes to 0 from the right of a to the power of 1 over x is e to the power of 1 over positive infinity, which is e to the power of infinity. And since e is larger than 1, this is simply infinity. That is a vertical asymptote x equals 0 from on the right. And what is the limit as x tends to 0 from the left of e to the power of 1 over x?
1, 0, like -0.
So it's e to the 1 over -0 because we come from the left. Which is e to the power of minus infinity, which is 1 over e to the infinity, which is 1 over infinity, which is 0. And you clearly see it on the graph. And that's one of the main reasons, excuse me, that I don't like the term asymptote. Because in high school, in Israel, high school, right? The question will be whether there is an asymptote or there isn't an asymptote. The students will say there isn't an asymptote from the left, but completely ignoring the fact that he found the limit. The limit actually tells me how to draw the graph. I need to send the graph on the way to 0. You agree? So what I care about are the limits, whether there is an asymptote or not, does not matter much. Okay? And on negative infinity, the asymptote is also 1, because 1 over negative infinity is again 0, e to the 0 is 1. I won't write that. I'll write it. It's the last one. It's the last limit. And lastly, the limit as x tends to negative infinity of e to the power of 1 over x is e to the 0, which is 1. And therefore you get all the nice, interesting limits you see here on the graph. Where do I usually calculate limit? When the x goes to infinity or minus infinity, and at points of no definition, because it's a specific case of discontinuity. The points I'll always wish to find the limit are points of discontinuity when I'm not sure what the limit is. It's not actually the value of the point of the function at the point. Okay, any questions so far about the idea? Yes,
It's more about the specific calculations that
yeah,
you did e to the 1 over 0 minus 0, -0.
yeah,
And that equals e to the minus infinity.
yes.
I
Yes.
understand that you can't. You're when you do the power to the power of minus infinity, you're treating that like the other kind of values that powers have, which is when it's negative, you put it under a
Because it's
fraction.
not actually infinity. That's why I also write it within the brackets. It's just a shorthand of saying stuff. But going to infinity, meaning very numbers, very small. I don't like to call them small, but numbers very close to negative infinity. So these are numbers with a big absolute value, yet they're negative. So the 1 over x for values of x other than 0 actually a very negative number. And for a very negative actual number, I can use that. Right? So I don't use the rule in the limit. I use the rule in the way. In a sense, you can write it's 1 over e to the minus. I'll write it in a second. You can write it's 1 over e to the power of minus 1 over x. And that's just algebra when it's defined. Do you agree? That's equals, I didn't write what it's equal to. That's e to the power of 1 over x. So that's just algebra. And then I'm saying, think of me doing that, and then me saying, oh, so if this is minus 1 over x, it's actually 1 over positive 0. Because x was negative, you do a minus and you get positive. And then you get the theorem we did in sequences. 1 over positive 0 is infinity. Okay, so we don't need to write all of that. We just write the shorthand here. You are correct that pedantically we need to prove every one of these steps, I think. And we don't do all of them, but we did enough. Okay. Any other questions? Okay.
What's that last thing that you wrote there? Yeah, that.
What? This or this?
Yeah, was that the one you
That?
said? Yeah.
Another limit when x goes to negative infinity. It's the last of the graph, right? I've shown you what happened in infinity, happening 0 to the right, 0 to the left, and jokers to the right of me. And at minus infinity, yeah, I think about it all the time when I hear people speak. Sorry, it's not being I meant in politics. I'm not.
Reservoir Dogs.
What?
Have you watched Reservoir Dogs?
Elves. Great movie. I like the scene when they play
Play the
this song.
song. You like it?
Yeah, man. I told you, but no, okay. Yeah, it's a good movie. Come on. Saying that I would do the same. I'm a gentle soul. Any questions here now? Okay. So for the definition, and these definitions, we will have two equivalent definitions for limits of functions. For homework, you may prove that they are fact equivalent. I won't prove it here. And we will use each of them when we like it. Okay. One of them is simpler, so we like to use it a lot. The other one is the one with the epsilon, basically, which is a bit more I don't know, complicated, but is important. Okay. And we will see it also in calculus too. And we sometimes use it. Okay. So the first definition of limit by Cauchy and area.
You mean the guy or the series?
What?
Cauchy was also a guy, I'm supposing, like he
Yeah, he
wasn't
was a guy.
Yeah,
He was just a guy. It wasn't a series.
yeah. I mean,
You mean sequences?
yes,
Cauchy sequences are named over the guy.
yes, what I'm asking is it's using this or it's just by the same guy?
Same guy.
Ah, okay.
The definition of limit by Cauchy and areas or epsilon delta. What this is called.
I don't like it.
Yes, this is the least favorite. We say that the limit as x tends to x0, fx is L if for every area of L in which axis is the area of L,
X. Oh, why would it be X?
on the Y axis, right? Because we said that the limit is x goes to x0, f of x on the y limit goes to L. So for every area of L on the y axis, and before I will continue, I wish to show you the GeoGebra. I wish to think about a nice function.
Great. What a nice function.
Right? I agree. So let's think about this function here.
It looks like the top of a bread loaf.
Yes.
What a weird water droplet.
So let's look at this function. Would you say this function is continuous?
No, I mean,
Why?
from this point of view?
Yeah, looking at this.
Yeah.
Then is it continuous
No.
in this domain? Not talking about other domains. In this frame, from I don't know, minus 0.8 to 0.8.
You're going to say
Is
that
it
when it
continuous?
gets to 0, it goes to infinity and then back in the next one or something?
No, it can't. It's continuous in this domain.
Oh, no, wait, you can't, oh, wait, no, wait.
Right.
That's some-
Right? First of all, you see the point here?
Oh man.
No, but it is continuous.
What is so? You just said it wouldn't be if there was a point. I'm showing you the point. No, but it is continuous. But that's very interesting that it puts the point here. Because what is the y value of the point where the function is undefined? So obviously one, I have no idea why he's putting it here. Removable discontinuity. Now I have an idea and I have less respect for it because it's completely wrong. The removable discontinuity is not at 0, 1. As you can clearly see looking at the drawing. Yes, it says that's the point here. Oh, it's here. No, he's wrong. And you're wrong, and everyone's wrong. That makes me happy. And
It's to infinity.
no. I want to see the point.
Other one. On the sides.
Okay, now I can do green screen without
It's
And
each,
only part.
each of the cosine of x times. I don't know, minus 1.
What would you say from this drawing is the limit of this function at x tends to 0?
1.
No point.
No,
No point.
no, it's not 1. That's a semi-answer, right? It's not even true. But what I mean is, why did you say 1? Because you say the actual value is supposed to be 1. But it's also false. What does it look like? It's 0.6. It looks like 0.6, right? But wait, if we zoom in, we'll see it's not 0.6, but
0.61.
I wouldn't expect you to, well, I do expect you to be able to calculate it, but I didn't give you time to. So is the limit 0.6? So let's take an area around 0.6. Can you give me an area around 0.6?
0.5, 0.7.
Great. But it's on the y value. So I write y equals 0.5, while y equals 0.7.
So first we get to 0 sides.
So first of all, would you say that the function is always within that area?
No, it isn't, right?
We see it now. No, I'm not saying, this area between the purple lines, between 0.5 and 0.7, is the entire function between these lines. No, like in sequence, when I told you the sequence tends to 1. So we took some area of 1, and then we asked, is the whole sequence within the area? The answer was no. What did we say in sequences? What was the demand?
It's the number of points.
Yes, so numbering here would be completely useless, right? Because there is infinite out and there is infinite in, not good. The way I worded it was from some point forward, right? But what is forward here? What is from some point forward?
Closer to whatever we set the limit to be, or
So can you tell me when, at which place is the function actually between the purple lines?
minus 1.2 and 1.2.
And what do you call it in general? Minus 1.2 to 1.2. What would that be?
Modular 1.2.
An area of
Your
who?
epsilon. No, not epsilon.
Yeah, there will be. Epsilon is the width of the area. It's half the width. It's the radius of the area. But an area of who?
That's
Of the x on the x-axis. Exactly. That's the definition. That's the definition. Okay.
So
Wait, hold on. It's a print screen. Okay. So for every area of L, there exists an area of x0, but not an area, but a punctured area. Why? Because I don't care what happened at x0 itself, right? At x0, the function may be undefined, somewhere else, I don't care. So we call it a punctured area of x0, such that for all x, and I also wanted to emphasize that this area is on the x-axis, such that for all x's within the area of x0, the y values f of x are within the area of L. That's the definition. It's also a generalization of the definition of limit of sequences. It's just that the area of infinity is from some point forward. I will emphasize that in a few minutes. But I wish to go on the drawing. So like Thomas said, if I write x equals minus 1.2 and x equals 1.2, and now put mark them in the same color. This is ugly. Yeah, yes, it's cute. And it's not exactly 1.2. Let's do 1.1 to be extra short. So within this area on the x-axis, the y values are within the area of the y-axis. Agreed? Now, is it enough that it works only for this specific area?
No.
No, we need it to work for every area, right? So now let's take a much smaller area. 0.59 and 0.61. And let's zoom in. What? What? Oh. I was wondering why is it's not symmetrical, and then I got because it's not the actual limit. But it still works, right? It still works. If I'll take minus 0.1, oops, minus 0.1 and 0.1, it still works. Agreed? I have to take a even smaller, even a bigger zoom in, smaller segment, I don't know, smaller resolution. So 5.99 and 0.601. Aha. Would you say now?
We screw that.
Yeah, it's not the limit. We took a very small area around 0.6. And it's not the limit. It's not the limit.
The
Agreed?
boundaries.
What is the limit is another thing altogether. We'll calculate it in a bit. I'm just trying to show you the idea of the definition of a limit. If it was the limit, then no matter what the zoom I do, I will always be near in the area of 0.6, right? But here I'm not. When I zoomed in, I'm far above 0.6. Agreed? Because it's not the actual limit, we'll calculate it a bit. Yes.
Series be a function.
What?
Can a series be a function?
No, a series is a series. A function, like in discrete mathematics, is for every x, you get a value. If you take a series with the number x within it, like I did, like the series of x to the n, will be a function. Because for every x, you define it as the limit of the partial sums and sequence. Okay, so what is the actual limit here? Let's calculate it together. And I do need Thomas's help here.
Oh, how am I going to screw up today?
Yeah, you're going to say, I have never seen it. You did say it, but no. Let me write the question first. So this is the function. First of all, looking at it, I hope you see why 0 is not in the domain of definition, right? You're not allowed to divide by 0. So it's obviously is not a continuous function. What is the limit? So what is cosine of 0?
0. No, 1.
1. What is the limit of 1 over x squared? It's 1 over 0. But what kind of 0? Are you sure the sign?
Yeah, it's positive because it's square.
Because it's squared, exactly. So it's 1 in the power of infinity. Do we have any tools to handle?
If we do, I haven't seen them before.
Never in my life.
Never in my life.
N to the BS.
Sorry.
is e to the-
We do the
e to
limit as x
n
goes
and
to
then
0 of, no, sorry, e to the power of limit as x goes to 0 of the power times the base minus 1. Okay, remember the E rule. If an goes to 1, then write a sentence. If an goes to 1, then
and
an,
and BN.
I don't need anything about the n, we talked about it. then an to the power of bn tends to e to the power of the limit of bn times an minus 1. Okay. And we saw it for sequences, but I will show you a definition of limits of functions using sequences, which makes it possible so that almost every theorem we learn about arithmetics of limits in sequences will also be true with functions. So for now, we just believe in it, but later I will explain why is it true. And now we need, and Sami, you're gonna like that, we need to calculate the power in the limit, excuse me, of the power, right? So do you know why it's going to be interesting?
So it's like the same thing.
No,
It's the same problem.
no. This is cosine of 1 of x minus 1 over s squared. Where does the numerator tends to? And the denominator? What do we do when we have 0 over 0? L'Hopital.
Yeah.
We obviously did not learn it, but so 0 over 0, you can do L'Hopital, which means deriving, taking the ratio of the derivative, right?
So clever.
Yes, that's mathematics.
Maybe.
And that's minus sine of x over 2x. What do we have here?
Another
0 over 0. Let's do L'Hopital. So that's the limit as x goes to 0 of minus cosine of x over 2, which is minus half. Therefore, the original limit is limit as x goes to 0 of cosine of x. I love this example. Over 1 over x squared is e to the power of minus 1/2. I can't believe you didn't get it yourself.
Obviously.
It's 1 over the square root of e, and you called it 0.6. But at least you weren't as horrible as GeoGebra, which rounded it up to 1.
Of course,
0, 1.
of course, pi is 3 and the gravitational constant is 10.
Yeah.
I'm an engineer.
But even if e is 3, that's still square root of 3. It's not 1 in any way. Okay, so now let's zoom out and let's, okay, not that much. And let's put the limit where it should be. So L would be 1 over the square root of e. And here I'll do L plus 0.01, and that would be L minus 0.01. And what do you see here, guys? It actually works because that's the actual limit. And it doesn't matter how small the addition will be. When we zoom in it enough, the function will be there. Read. Let's write this definition in an algebraic form. And what do I mean? Let's ask ChatGPT, what is the definition of a limit of a function by Cauchy. And he wouldn't write to me the area thing that I described. Let's see what he would say. Not sure, I never searched for it, but let's see. By the way, it does do domain instead of definition domain, like I told you. He said the limit is for every epsilon there exists a delta, blah 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 blah. That's all I wanted to show you, right? That's what I mean by writing it algebraically. It's not a different definition. Many lectures start giving you that formal thing, but I think it helps to understand what we're actually saying using this algebraic notation. So we said that for every area of L, there exists an area of X0. So what separates different areas? The radius. So the radius on the y-axis will be called epsilon, and the radius on the x-axis will be called delta. That's why it's called the epsilon delta definition. For every epsilon, there exists a delta. For every choice, zoom in on the y-axis, there is a matching possibility to zoom in on the x-axis. Okay, and I'll write it. We say that the limit of x going to when x tends to x0 of fx equals L, if for every epsilon, positive epsilon, which denotes a radius on the y which denotes a radius on the y-axis. There exists a delta, positive delta, which is the radius on the x-axis.
Surely there's a better way of writing that in mathematical notation.
In what?
A radius on the x-axis and a radius on the y-axis. Like, is there not a better way of writing that?
I don't need to write it. It's just for you to understand.
Oh, okay.
If you want me to write it in mathematical notation, I will do it in a second. It's horrible, but I will. It will be a reminder of discrete mathematics. In a second, there is something interesting about it, to be honest. We say that the limit as x goes to xfs such that for every x, if the distance between x and x0 is not zero, that's why it's a punctured area, not including, not looking at x0 itself, but still smaller than delta. That's the mathematical notation you spoke about. Now it's actually written. Here I can understand why delta is a radius on the x-axis, because I measure with it a distance between the x values. So if it's true, it is true that the distance between f of x and the limit is smaller than epsilon. Okay. And in complete logic notation, I will write for every positive epsilon, there exists a positive delta, such that for all x's if x minus x0 is smaller than delta, then f of x minus L is smaller than epsilon.
Hmm.
So I could have started just writing that. I think it's counterproductive. Okay, but that's the that's the most pure mathematics. It's not the most pure because this should be turned into two that is different than 0 and is smaller than. I think that's mathematical enough, right? And I wish to go with the ChatGPT with this to the ChatGPT and show you. It's more about discrete mathematics than calculus, but this is the point where the two meet. Then when we change small things here, we get different things. You'll see. So if I go to ChatGPT and ask him, what does this definition says? So this is the Cauchy epsilon delta of a limit. Okay. Now I'll change it up a bit. And instead of L, I'm going to write f of x0. What do you suppose that will be? Instead of L, I write f of x0. And I ask him, what did I define now? That's continuity, exactly. What? Okay, so he didn't say the answer. So it looks similar, but there is a difference. Let's look at it closely. Yes, okay. This is the definition of continuity in the point x0. I wish to do a couple more. So, like I said, f of x0.
This checks only at a certain point if there's continuity.
At x0, that's a very good question because that's the next twist and turn I'm about to do. So that it's smaller and try to get in the same line for the next as well. So this is limit. This is continuity. And the next one would be, let me just say that's continuity at x0. Now I wish to write for all x0, this is true. So what do you think that rule will say? Continuity everywhere, right? Because I'm saying for every x0 there is continuity, right? Let's try it with the ChatGPT. Just tell me why it is. Interpretation. This is a global set statement. It's asserted that the function f is continuous at every point of its domain. Great. Now look up closely. It's also an exercise in discrete mathematics as well in calculus. I'm taking this definition and changing it up a bit. Look up. I'm taking this part. There exists a delta, and moving it up here. Will that create a change in the definition?
Yeah.
What kind of change?
Access change.
It means,
So I just changed delta. The algebraic expression is the same, right?
yeah,
I
so
didn't touch the algebraic expression, which says delta is for x and epsilon is for y.
for every range of x, there exists
It's literally not what's written here.
not what's written there.
No, it's written there exists a delta, and you start with for every
About
x.
the image,
You
maybe.
were read you have read you have read this, right? This is there exists a delta such for every x, fs, every epsilon, it will work. So it sounds a lot the same. Let's use ChatGPT here.
It's one delta for every x.
It's the same delta for all the x's. What? Statement is false.
That's the wrong type.
Wrong chorus,
right?
that's for sure. There's this-
Oh, the domain is limited. Is that what it's saying?
Too strong. Oh no.
The ChatGPT very mathful than maths.
Wait, I think, ugh. I did a mistake, not him, oof.
That's-
I thought that
That's
I needed to move that as well. He was right. I was hoping to catch him on there. Okay, so I need to move both of them. For every epsilon, there is a delta. Okay, sorry. Sadly mistake.
I apologize to us. Apologize to them.
Yes. No, yes. For every epsilon, there exists a single delta, such for all the points it will work. What this implies, this is the very strong uniform closest condition. No. I'm wondering why is it not? Yeah, that's the definition of uniform continuity. Almost. Why almost? That's the definition of uniform continuity.
Damn it, I understand now what you were saying before I mentioned.
Yes, that inside. I wonder why I said that when I think I'm now more cautious about it, but I think he has a small mistake when he says it's not uniform continuity. But I don't wish to
under the
chase it
machine
any
codes.
further. That's uniform continuity. Continuity. Let me just think of it. For all x, only the difference. That's this. No, I think it's a completely equivalent. I agree that I would write it a bit differently, but it's completely equivalent for continuity. Because if x actually equals x0, then this is obviously 0, and this obviously is true. In any case, the point is that the quantifiers from discrete mathematics are so important. Their order is important. Sometimes the mistake students do when they deal with limits is just looking Well, actually, they just look at the last inequality, right? But the quantifier is so important. Not every continuous function is uniform continuous. These are very different definitions. And what is interesting about it is in discrete mathematics, quantifier seems like a hard concept to grasp. And many times students say, and it has nothing to do with the other courses, but actually the course when you have the most complicated examples of quantifiers is calculus. You will never see something like that in discrete mathematics, but in calculus you do. Okay, uniform continuity by itself would be something you see in calculus too when you learn about integrability, right? So all these concepts are a bit different, and the quantifiers are very, very important. And the simplified version is the word version. It takes some of the quantifiers and put it into words, right? To say for every area instead of for every epsilon. And it's a bit easier to understand, and it also takes the algebra out. Say the y values are within the area. Okay, but it's mathematically it's completely equivalent. Okay, any questions so far? Yes, Thomas.
I'm looking at the definition of continuity and I'm not fully getting it because
It's fine. I didn't define continuity yet. I will answer you anyway, but it's fine because it's just like introduction. But I'm saying that the distance between the value of f at x and the value of f at the actual point x0 is small.
what's x0 in this context?
That's the pointer at which the function is continuous. That means that the limit is equal to the value of the point. It's here. I just plugged in, substituted. Instead of L, I wrote f of x0. Simply means that the limit is f of x0. And that's what we said. It's continuous, but the limit is the value at the point. But we'll do continuity later, right?
Sure.
I just wanted to talk about the quantifiers. That's the thing.
So
Yes.
right now, the only thing we actually need to know is the topic.
Yeah. Yes and no, because you learn discrete mathematics already, so you need to understand all of them. No, but in all seriousness, yeah, that's the point of today's lesson. The limits of functions and not the other concept. This I will not even cover this semester. And this is easy because I'm just saying continuity everywhere, right? And this is easy as well, but we didn't define it. Yes, I didn't fully define continuity. Okay. Next lesson, it would be lecture 15. Not did I write? Yes, it's lecture 15. I will start with Heine. Not sure how you say it in English. Not sure how you write it in English.
Heineken?
You're so drunk. Echt in Heine Banglitz. Sure I didn't write it correctly. I did write it. Heinz, and probably Hein. I will read it, I'm not sure. Never heard it in English. Heinz, Hine? No, you're guessing, I'm not sure how you say it.
It's right.
Yeah, Heinz definition of limits of functions using sequences.
Yeah, it's H-E-I-N-E.
No, I checked it already. The
Okay.
next question was, how do you pronounce it? And he says Hine, which is nice, but
Ine.
Hine, Heine, but yeah, Heine,
Did this guy also make mayonnaise or is it a different kind?
Heines,
That joke already.
yes.
Copyright.
I prefer the beans actually.
It's funnier.
Yeah, no, you said beer.
And then I said mint.
That's how I do know.
Yes, Heineken. It's a can of Heineken. Next session. Have a good day.
Do we have functions on the red one?